I think it said recording in progress. All right, cool. Okay, so I've been mentioning like we've all seen linear algebra before, but one thing I'm going to really emphasize is that this interpretation of matrices in terms of dynamical systems is extremely useful for getting intuition, not only for what some of these sort of esoteric theorems like rank nullity really mean, but they also explain a lot of methods that are used in practice to calculate properties of large matrices. So there's an entire class of algorithms, they're called Krylov subspace methods, that basically treat whatever matrix I'm trying to analyze as implicitly defining a dynamical system, the properties of which I analyze to get my matrix properties. Today, we're going to talk about the QR method for finding eigenvalues, which is one example of a Krylov subspace method. But there's an entire universe out there of algorithms that take a matrix, say this defines a dynamical system, and then deal with the consequences of that idea. Okay, so the one critical thing to think about if I want to think about a matrix as some operator that acts on a space, on a dynamical space, is that if I have something like a Hermitian matrix, that matrix implicitly defines a stretching operation on a bundle of points subject to the matrix. So the idea is that if I have a symmetric matrix, if I have a bunch of points, maybe they're initial conditions of a dynamical system, or maybe it's something more abstract like points in some elastic solid. When I apply one iteration of a matrix to that set of points, that defines sort of an anisotropic deformation of that set of points, where the directions of that are the eigenvectors, and then the amount of stretching are the eigenvalues. So any symmetric matrix you can interpret in terms of directions that your operator is stretching your point cloud among, and then the amount that's getting stretched in every direction. So the classic example of this would be maybe I have a bunch of initial conditions and I just blow them up. So maybe I take a circle and I just expand it uniformly in all directions. So in that case, I haven't actually deformed it, right? So that means that my eigenvalues are just going to be my unit axes. And my eigenvectors are my unit axes. And then my eigenvalues will just be the amount that I blew up my thing by. So a diagonal matrix, which is by definition symmetric, just corresponds to a uniform stretching along my existing axes. And this is nice because this is the whole idea behind not just the QR method, but also a lot of these Krylov flavored algorithms, is they're really trying to find these stretching directions and dealing with things in the subspaces defined by the principal stretching directions. So what this diagram is showing is that if I have a unit circle, I apply some, in this case, symmetric matrix to that. If I have one eigenvalue that's really big, that's going to be the principal stretching direction, and this will be associated with some eigenvector that defines a stretching direction. So eigenvectors and eigenvalues define directions and magnitudes of this deformation. And because Hermitian matrices are invertible, you can always undo a stretching, so you can always go back, and the eigenvalues are 1 over because you're unstretching by the same amount. Okay, so that's the canonical interpretation of Hermitian matrices in terms of dynamical objects. Okay, so the reason I mention this is because in principle, if I want to find the eigenvalues of a really, really big matrix, usually this isn't going to work the same way that it does when we usually learn how to work with large matrices, or how we work with spectral decomposition of matrices. Right, so I don't know how everyone else learned this, but when I was taught eigenvalues, I was taught that you take your matrix, you subtract this like set of algebraic terms where this lambda is an unknown variable. This will define a giant linear system and with n unknowns for n variables and n equations. And I was basically taught that that is a giant like linear system. I find the determinant, that gives me a giant polynomial. And then the roots of that polynomial give me my eigenvalues, right? This is the canonical view of how we actually find the exact eigenvalues of a large matrix. But if you think about this kind of mechanistically, right? If I gave you like this 4,000 by 4,000 collaborator network of astrophysicists, this would be a pretty big polynomial, right? So, I can always set up that problem. I can subtract out the identity matrix with these unknown lambdas. And that turns out to be n cubed operations because it ends up reducing down effectively to a matrix multiplication. So that's painful, but not that bad. But then after I found that, I have an n degree polynomial, right? So I have a giant polynomial of order n. So I have to do a root finding operation on a really, really high degree polynomial. And that is actually extremely expensive to do either numerically or especially by hand. So in the same way that, you can easily find the roots of a quartic and sometimes a cubic, but once you get to, a quintic or something, it starts to get a little bit difficult to solve that by hand. Doing this for a 4,000 by 4,000 matrix is really not practical. So the schoolyard method of finding eigenvalues of large matrices is always exact, but it also is really not practical when you go to really high dimensions. Yeah, and root finding, I can't give you an order n complexity there because it depends on the algorithm, but it turns out that manually finding roots of a high degree polynomial purely using numerical methods, that's much, much worse than n cubed operations. Okay, so the question is, can we do any better? And the idea behind the algorithm we'll talk about today, as well as basically all methods that fall in the Krylov subspace family, is that we're going to exchange exactness for speed. And the idea here behind what we'll learn today, as well as most of the Krylov methods that are discussed in excruciating detail in the notes and in the book, is that I can basically control how much compute I'm willing to burn on a problem for a given amount of accuracy. So it's very similar to those of you who solve ODEs know that there's this famous trade-off between how accurate your solution is versus how expensive it is. And the same is true of all of these Krylov methods. I decide how long I want to iterate for. That's set by my compute budget. And the longer I go, the more accurate I expect to be. Okay, so Krylov methods, I should really just put Krylov here, but we're just going to say iterative methods. All of them are basically going to have the form where I'm going to take my matrix, I'm going to do something to it, I'm going to update it, and then I'm going to rinse and repeat a bunch of times. So implicitly, all of these Krylov methods define something like a dynamical system from the matrix. And the question is just how long I run that system is what determines the performance of my algorithm. Okay, so that's why we would want to find eigenvalues numerically. But the big takeaway is that this is the first example of an algorithm where, unlike LU factorization, we're actually going to deliberately get an answer that's slightly wrong in order to solve within a finite amount of time. So this is going to be an approximate algorithm, whereas LU was an exact algorithm. Okay. So in principle, finding the eigenvalues and the eigenvectors of a well-behaved full-rank matrix isn't that bad. And usually in linear algebra, we actually see how to do this explicitly. So when I learned linear algebra, and I imagine this is pretty standard, we basically learned one method for doing this, and this was the Gram-Schmidt method. So the idea here is that if I have a bunch of vectors that are implicitly defined in the column space of a matrix, Gram-Schmidt basically involves picking one of those vectors basically arbitrarily. By convention, we always pick the first of those vectors, finding the components of all of the other vectors along that vector, subtracting it out, and then moving to the next vector, subtracting out that vector's components from all the rest, et cetera, et cetera. So Gram-Schmidt has this aspect of being an iterative method where I pick a vector as my sort of bearing direction, I subtract everyone else's components along that vector from that vector, I then go to the next one, anything that remains, I subtract from the rest. And this will always work as long as A is a full rank matrix, so it doesn't have any columns that are the same to within some scalar of each other. Okay, so Gram-Schmidt is an iterative algorithm, and it turns out that if you think about that series of steps where you're going to take a vector, subtract its components from all the others, rinse and repeat with all the others, you can actually bookkeep that as defining two new matrices, one of which is your orthonormal basis. So this is this matrix that's been sort of purified to only point along your main directions. And then a set of coefficients that corresponds to what you subtracted out in order to derive each of these vectors. And we'll go through this in more detail. But the big takeaway here is that Gram-Schmidt, which we normally learn as a very iterative process, can equivalently be written as a matrix factorization, where I take my matrix that is some column space. These columns are probably not orthonormal to each other. And then I write it as a product of my nice orthonormal basis. This is what I want, as well as this series of terms that are going to allow me to recapitulate the original matrix. Okay, and the fact that it has this structure is going to allow us to write this algorithm down in a really clean way. Okay, so before we get into how we actually do QR factorization, I just want to show a simple example of what basic Gram-Schmidt looks like with just two vectors. So if I write Gram-Schmidt out just in terms of NumPy, what I'm going to do is I'm just going to find two random two-dimensional vectors. So these are just two vectors that probably point in different directions. And I just picked random here. And then first I'm going to start by just plotting them. So let me actually comment out everything so we can just look at those vectors. It's probably faster if I just do it like this. All right, so those are my two vectors. They point in random directions. They don't look like they're aligned, so I don't have a singular case or something. And this is pretty unlikely I get a singular case here. Okay, so those are my two vectors, and I want to use Gram-Schmidt to orthonormalize them. Okay, so Gram-Schmidt, the first thing I do is I decide which vector is my bearing vector. So here I'm going to use the red vector as my bearing vector. So I'm going to define this as the thing I'm going to perform an orthonormalization around. So the first step of Gram-Schmidt is to take my other vector and find out how much it's aligned with the existing pivot vector. I'm then going to subtract the component out from it. So in NumPy, that just looks like this, where I'm going to project. So that's just the dot product of my two vectors. I have to then divide by the norm of the vector I'm projecting onto. That's because this vector is not normalized. So I need to make this a unit vector. And then the other factor comes from the fact that I want this to be promoted to a vector. So I multiply it by that. So this is the same as writing the component along that other vector times the unit vector associated with the original vector, where vec1 is the red vector here, and vec2 is this blue vector. Okay, so this term should basically just be a new vector that points along here that is just somewhere like this, and it just tells us, how much of this vector aligns with that vector. So let's see if I got that right. Yeah, that looks good. Okay, and I plotted an extra vector there, it looks like. Oh, okay, because I'm up here. Okay, so this is my projection, and this is just me taking the dot product and subtracting out that unit vector. Great. Okay, and so then that's the first step of Gram-Schmidt, is computing that coefficient. That just is how much I align with this vector. And then the next thing I'm going to do is I'm going to define a new vector that corresponds to my blue vector. So that's this guy minus the green component. And that should hopefully get rid of all of my overlap with the red vector. So we'll see if that works. Yeah, and it looks like it works. Oh, it skips down a cell whenever I hit that. Okay, and it looks like it works. So all I do is I just find a number here. We're going to call that number R. Subtract out that along this unit vector, and this gives me that vector. And those are the three steps of doing Gram-Schmidt on two things. Okay, so then this idea that I can write everything I just did in Gram-Schmidt as Q times R, we're going to see that very explicitly here for this particular example. So all of those things I just did, I can group into a matrix. And the way that I'm going to do that is I'm first going to take my pivot vector. So this is going to be that red vector that I'm centering everything around. I'm going to go ahead and normalize that, right? Because I need an orthonormal basis. And I'm going to go ahead and say that's going to be my first column vector. So my first column vector is super trivial to compute. It's just the normalized pivot vector. Then my second vector is going to be computing that series of steps where I orthonormalize. So that's just where I projected, subtracted out, and got that orthogonal vector. Then I have to normalize that. And that new vector is going to be my second Q. So again, Q1 is just my pivot. Q2 is my remainder after subtracting that pivot vector, and that gives me my orthonormal basis. So my Q matrix is super easy to define. It's just my two vectors after they've been normalized. So that's no big deal. The really tricky thing with Gram-Schmidt is finding out the values of the R matrix. So the R matrix is symbolically defined like this. And basically all this is bookkeeping all of these individual projections I did in order to construct this, right? So in order to find this component, I had to do this step here where I did this dot product. So the R matrix just stores all of those dot products. So if I actually want to define my R matrix, I'm just going to put all of my remainders into it. And then the diagonal elements of that matrix are just going to be my normalizing factors for each unit vector. So all that the R matrix does is it bookkeeps all of these scalars I'm calculating to scale my vectors when I do this subtraction of terms. Okay, so another way of saying that is that the QR factorization of a matrix is exactly identical to Gram-Schmidt. It's just writing out the steps of Gram-Schmidt in matrix form. So if I bookkept all of those symbols separately, I would just get the exact same thing as if I manually did Gram-Schmidt orthonormalization. And you can verify that I did these series of operations of subtractions. I stored all of these things I did into this matrix R. And lo and behold, my factored matrix, if I multiply them together, gives me back my original matrix. Okay, so I emphasize this point just to say that as we saw before with LU factorization, in LU factorization, we saw that this L inverse matrix was exactly the same as bookkeeping all of these row echelon operations. So QR factorization is quite literally bookkeeping the steps of Gram-Schmidt. And so implicitly, you can guess then that the runtime complexity of this is going to be around n cubed because it's bookkeeping a bunch of operations. Okay, so that's all. QR is equivalent to Gram-Schmidt. That's the big takeaway there. Is QR factorization is Gram-Schmidt. Okay, so I just made this big assumption that my matrix was square, but it actually is the case that you could do this with non-square matrices. So the idea is that if I have some matrix that is rectangular, so it has more directions defined in its column space than it has columns. I can define sort of an augmented basis by finding all of the directions that aren't spanned by the row space and bookkeeping those as these extra sort of vectors that I pinned on to my full orthonormal basis. So I can always, for a given matrix, define the full orthonormal basis associated with the number of rows it has. But when I then go and I find my R matrix, I'll basically find I have a bunch of zeros because most of those vectors don't appear in the column space of A. So it's just worth remembering that even for rectangular matrices, you can still implicitly define an orthonormal basis. You just don't use all the elements. And we'll see this again in singular value decomposition, this idea that we can ignore part of our basis here by having a bunch of zeros. And then another thing is this is just a distinction because some languages do this differently. Some languages, when you do a QR factorization, they'll give you the full Q and they'll give you the R with a bunch of zeros in it. Other languages like MATLAB and maybe Julia, depending on which numerical linear algebra library you use, some of them will actually go ahead and crop this. And so they'll just give you a Q matrix that has the same shape as your A matrix, and then your R matrix will be square. And all this is just going between this representation and that. So sometimes it's useful to keep track of whether you're doing full or reduced QR, but this is the difference, is just whether I add on these zero elements. Okay, so what I'm going to do is I'm going to go ahead and implement QR factorization of a matrix, which remember is just the Gram-Schmidt process as just a function in NumPy. And all this is going to be is the series of steps I did for the 2x2 case, but now I'm going to have to do it for an n-dimensional case where n is greater than 2. So here I've written out like pretty extensive comments, but the idea is relatively simple. I have my matrix. I'm going to go ahead and transpose it because I want to have my first index be the index into the column space. This is just to make the code easier to read. And then at the end, I'm going to have to undo that. I'm going to pre-allocate my solution arrays. So in this case, I'm going to do full QR decomposition. So I'm going to go ahead and force Q to be a full square matrix. So these are just going to be initialized to all zeros. And then just like we do a normal Gram-Schmidt, I have to pick my pivot, which by convention is always going to be my first column of my input matrix. And you'll recall that the first step of Gram-Schmidt is just normalizing your first direction. So that's my first step, is just this. And then things are going to get tricky. So when I do two-dimensional Gram-Schmidt, right, I only have to do one step where I project my second vector onto my first and subtract out the component along that first vector. Now what I need to do in order to do Gram-Schmidt is I found my first orthogonal vector, and I actually need to project all of my remaining R vectors onto that vector and subtract it. So I'm going to end up doing a loop here, where the loop is going to be just the sum of the components of my original basis minus all of the orthogonal vectors I found so far, and I'm just going to project the elements onto that. And in the case where my index is 1, this will just simplify to the first step where I'm just doing a single dot product here. So this is just writing out the Gram-Schmidt process when you have more than one orthogonal vector that you're projecting onto, and it ends up being a sum over multiple elements. Okay, and just like we saw with Gram-Schmidt, I need to manually normalize the Q vectors after I find them, so that's this step. And then the R term is going to bookkeep either the projections that I performed here, so that's the elements of my original columns along each of those vectors, or in the case of the diagonal elements, it's just going to store these factors here that I needed to normalize my columns. So the diagonal elements have this nice structure where they just store your normalizing factors to return your original vectors. Okay, so this is Gram-Schmidt written out as a loop, and this allows us to do it for an n by n matrix instead of just 2 by 2 like we saw before. But the sequence of steps reduces down to that case we saw above. Okay, so that's Gram-Schmidt written as a function, and this will return the QR factorization where Q is our orthonormal basis set, and R is the series of coefficients you need to combine those vectors to get your original A matrix back. Okay, so QR factorization in Gram-Schmidt, I think probably everyone has seen in some form before. But the reason that this is useful to go through is that this basic intuition that I can write all the series of steps of QR decomposition in terms of sort of two matrix multiplications, this is the basic intuition behind the QR eigenvalue method. And this is a little bit of an overloaded terminology. So the QR factorization of a matrix is just Gram-Schmidt, but the QR eigenvalue method is a method of using the QR factorization to find the eigenvalues of a matrix. And I argue that this is going to end up being a nice way of finding it because it's going to allow us to basically keep performing QR decomposition in order to find eigenvalues without having to do this really painful sort of schoolyard approach where you solve a very high degree algebraic equation. Okay, so the QR eigenvalue method is actually super, super simple, which is I'm given my initial matrix, I perform the QR factorization, and then all I do is so I know that Q times R gives me A back. So instead of doing that, I actually just swap the order. I do R times Q, and I use that to update the value of A. So you can actually modify your matrix in place if you want, and just keep updating the values in that matrix's column space by taking R times Q. And this is kind of subtle because if this is just QK times RK, then this would basically just give me AK back. So the fact that I'm swapping these two is going to be what actually changes my matrix over time. And my claim is that by doing this repeatedly, so I have my matrix, I do QR, I then change my matrix to R times Q, so I just swap the order. If I do this enough times, I'll eventually find both the eigenvalues and eigenvectors of my original A matrix. That's the claim behind the QR eigenvalue algorithm. Okay, so that's the idea behind it, and I think I talk about how it works down here. So we'll implement it first, then we'll talk about why on earth it's the case that doing R times Q gets you closer to an orthonormal basis. One thing I'll just point out is that recall that Q is just an orthonormal basis written as a series of columns. And recall that orthonormal bases are equivalent to rotations. So what does that mean? It means that if I take a matrix and I rotate it by Q, if I then rotate it again, I can compose those rotations and get another orthonormal basis set. So you should think about Q as maybe defining a rotation as one way to get some intuition here. Okay, so this algorithm is 3 lines of code, so we'll go and implement it, and then we'll talk about why it works. Okay, so my QR eigen decomposition method, which uses the QR factorization, is going to have just a couple of steps. It's going to have a QR factorization method. So this is just going to actually do the Gram-Schmidt. And then it's just going to have a loop that for some really large number of iterations, it's going to do the factorization, do R times Q, and store the result in my X. And so it can even modify my matrix in place. And all this stuff that I have here is just me bookkeeping various things. So for example, I wanted to return the eigenvalues in order. So I go ahead and I sort them and all that. But this stuff is not critical to the algorithm. It's just sort of things that make it nicer to work with. Okay, So this is the core of the algorithm. And then the other thing I have here is you can see I update TQ by composing it with the current value of Q. This is just this line here, where I'm aggregating all of my Q rotations into a single combined rotation operation. Okay, so the QR algorithm and this code here is quite literally a copy paste of that Gram-Schmidt implementation I used above. I've just put it as a method within this class. Okay, so that's my implementation. Let me go ahead and get that into memory. Cool. Okay, so I'm going to go ahead and do this. And the way I have this structured is I have it as a class where I'm going to initialize uh, as arguments associated with the class or as class variables, the eigenvalues and eigenvectors. And then I'm going to have a flag that's going to allow me to store all of the intermediate values of Q, R, A, and T. This is just so I can see how they're changing during the algorithm. So this is not necessary. This is just so I can see what the iterative algorithm's doing. So I'm going to instantiate it. This is just me defining how I want to use the algorithm. And then I just call my find eigensystem method, and this runs all this code. Okay. So when I implemented this, it worked last night. So hopefully it still works. It looks good. So these are what the eigenvalues that the QR method gives me. And they appear to match 1-to-1 with NumPy. So this more or less gives me the right answer. So at least the QR method seems to work here. And it seems like it was pretty fast even for we could try going to like a 1,000 by 1,000 and we'll see if I regret this. All right, we'll let that shoot. And one thing I'll mention is that I have a maximum iterations here. So this would be the argument I would adjust if I wanted to, for example, have a higher precision eigenvalue calculation at the expense of having a lot longer runtime. So runtime is linear in the number of iterations of Krylov methods. Okay. Yeah, I thought I would regret that, but we might as well just leave it running because I'm not running anything else right now. Okay. Let's get that over there. Okay. So the actual reason that this QR eigendecomposition method works basically is because you can think of the R matrix. When I perform R times Q, you can use a little bit of linear algebra to show that that is equivalent to writing Q inverse times our original matrix times Q. So you can write R as Q inverse A. And that makes sense because A equals QR, right? But the reason that that's nice is because if Q is an orthonormal basis, then that means that this is essentially a change of basis, right? So R times Q is equivalent to doing Q inverse AQ, which you'll recall is a change of basis in linear algebra. So what that means is that basically whenever I do this R times Q, I'm just rotating all of the vectors in the column space of A by a very small amount. That has to do with the magnitude of the values here. So I can almost think of my RQ operation as sort of a series of very gradual rotations on the column space of that matrix that very gradually align all of my vectors with the actual true orthonormal basis. And so asymptotically, then that's great because that means that over time, if I do this enough times, eventually I'll get a situation where where A is perfectly aligned with Q. And so then I get my original eigenvectors back. Okay. And so that's the basic idea behind why QR works is I'm just constantly gradually updating. If I have like a bunch of vectors, I'm gradually forcing them to get more and more orthogonal to each other by aligning them with this continuous change of basis. And it turns out that as a free side effect of that, by the time I'm done doing this, my R matrix will just have diagonal elements that just equal my eigenvalues. So these scaling factors that I have to keep performing when I do QR end up being equal asymptotically to the eigenvalues. So it's a very nice algorithm because it turns out that it just uses a couple of lines of linear algebra to prove that it converges to the exact answer. Okay, so I'll mention that I do this in terms of Gram-Schmidt. The book has a completely different way of doing this using a householder reflection matrices. I don't think that these are as intuitive, but if you don't like the Gram-Schmidt method, you might find this more mathematically satisfying. But one thing I'll just mention is that the power method, which is one of the two homework problems, the power method is a simplified case of the QR algorithm. So the QR algorithm gives you the full eigenspectrum, and the power method gives you just the leading eigenvector. Okay, so we'll go ahead and skip the unit test thing because I don't think it's very interesting. I'll mention if you're interested in Python software development, you might read about test cases because I show an example of how to use it here. Okay. So you'll recall I set this flag that stored all of the intermediate values of Q, A, R, and all these different terms. So now we're going to use the fact that we stored all of those to actually visualize what each iteration of this QR algorithm does. And hopefully this will work. Okay, so these are my original two. So I think I did a 2x2 matrix here. Oh no, here I'm doing the 100 by 100, so I've got to kill this calculation. So let's go ahead and go back to something less painful. Great. Okay, and it looks good. Okay. Okay, so here what I'm going to do is initially when I run this, I'm just going to get the first. I'm just visualizing the first two components of my vector because it's too painful to do this in a 10-dimensional space. So my first, initially the two columns look like this. So they're not aligned. I don't have an orthogonal basis set. It just kind of looks like this. But the QR algorithm, every time I update this slider, just corresponds to a single call to this loop here, where it calls this loop, which implicitly performs this Q inverse AQ step, which is going to then try to align these two vectors with the principal, with the eigendirections. So that's why I start out, then I go forward one. Already I'm doing pretty good. Then I'm basically done, and then it converges. So basically this converges within 3 or 4 steps to the exact solution. And I mentioned that because you'll recall that the runtime scaled with something like the number of time steps, and basically I had to do 3 time steps to get to a pretty satisfyingly close approximation of the true eigendirections. Okay, so this whole linear algebra thing means that this converges super fast, and this is almost always true for Krylov subspace methods, is that there's guarantees on how fast they converge. So usually there's no floating condition where you might have to run this for infinity steps. Usually they have some guarantee that they converge in a finite number of operations. Okay, so these are the steps of my QR algorithm, and it looks like that. And then if you draw that out, you can sort of see what's happening here. And I'll mention that 2 things are happening here, right? You can see these vectors are getting more orthogonal, but they're also stretching. And that's because they need to both be unit vectors for this cube basis. So that stretching comes from the diagonal elements of the R matrix. So the diagonal elements tell you how much these vectors are getting rescaled.
Okay.
Yeah.
So I don't understand why it is converging to the eigenvectors. I understand it's a rotation, but couldn't have been like some rotation that makes it go up. Like what makes the rotation like make the basis of rotate to the eigen?
So I think it's because so I think that this is getting into the fact that I force it to align with the coordinate axes using this second calculation of t. So this t kind of aggregates all of the rotations I've performed the entire time. And so the nice thing about that is then all of my rotations aggregated is just some other rotation, and this ends up being the rotation that aligns me with the coordinate system that I'm using, the principal directions or whatever. So I would actually still get the right eigenvalues if I didn't do this. I just would get eigenvectors that were pointed in the wrong directions. Yeah. Okay. So then one thing that is nice about Gram-Schmidt, right, is we're talking about the column space of a matrix, right? And we're talking about how that gets more orthogonal if you repeatedly apply some iterative operation. And you remember I had like a 2-lecture rant about how when I have nearly aligned columns, really bad things happen. And it turns out that you can actually link the condition number of the matrix that you're trying to perform QR factorization on to how accurate the QR eigenvalue spectrum is. So here what I'm doing is I'm going to do the same trick I was doing before, where I'm going to deliberately define a matrix to be very close to singular, but not quite. And I'm going to do that by building a 4x4 matrix where every column vector is the exact same vector plus a tiny amount of noise that disaligns them. So when that noise is some really, really small number, I have a nearly singular matrix. So it's a high condition number or an ill conditioned matrix. But if that noise is some really big number, basically I have 4 random vectors, and so I should have a matrix that probably has full rank. So I'm going to just manipulate the condition number and see how that affects QR factorization. Okay, so let me see if it worked last night. So let's see if it still runs. Yeah, looks good. Okay, so the first case here is the case where I have really high noise. This is basically just a random matrix, which will usually have full rank. So my condition number was order 10, which you'll remember was roughly consistent with what we were seeing for the well-conditioned problems before. And the error versus the versus a more elaborate, the error in the QR reconstruction versus the original matrix is pretty small. That's pretty close to machine precision. So that's great. So then I'm going to do the exact same thing, but now I'm going to have really, really small error, which means that this matrix that I'm doing the QR decomposition on is going to have almost parallel column vectors. And when I do that, my condition number is now crazy high. And my error, it's still small, but it did go up by 7 orders of magnitude. So having a high condition number, I very clearly paid a price here in terms of accuracy. So ill-conditioned matrices will throw higher errors when I do QR factorization. Okay, so the intuition for why that might be the case is here I start out with these my two column vectors were pretty misaligned here. So the case here where I have a tiny amount of noise here basically corresponds to the case where my 2 column vectors are almost the exact same here. So all of my dot products are extremely close to inner products, which means that I'm subtracting really, really tiny numbers from really big numbers, and that's a recipe for a numerical disaster. So the case where, so if I had these 2 starting vectors be really, really similar to each other, I'm trying to stretch them apart when they already want to be together. That's the case where I get really high numerical error because they're already so close to being aligned that disaligning them hits my precision floor. Okay, and this is what motivates a pretty simple modification of the Gram-Schmidt process. And this is different than the way that we normally do this in traditional linear algebra. So the intuition here is that if I have 2 really, really similar vectors, if I do this dot product, I get a big number. I'm then subtracting that from the original vector, so I'm subtracting a small number. And so as a result, I end up with this sort of mismatch of scales where I'm constantly subtracting big from small, and that gives rise to numerical errors. If I want to mitigate that, the one idea that I might have is that the moment I find an orthogonal direction, so for example, when I pick my first direction, my pivot direction, rather than storing that and then calling it every time I want to orthogonalize a new column, instead, the moment I find that vector, I'm going to subtract that out of all of the remaining columns. So in other words, rather than doing sort of a backwards looking algorithm where every time I find, I might just go to the diagram because I think that that's the easiest. Every time I find a new Q direction, rather than storing that, then I move to here and I subtract out the component along here. Instead, what I'm going to do is I'm going to find a direction here, and I'm going to immediately find all of these components along that direction and subtract it out. So the moment I find a new orthogonal vector, I'm going to remove the component along that vector from everyone. And the intuition there is that that's going to mean that in every step of the Gram-Schmidt process, I'm going to make my column space a little bit more orthogonal by getting rid of all of the redundancy with the unit vectors I've already found. So that's the idea behind what's called the modified Gram-Schmidt algorithm. But what that actually looks like is actually pretty nice, which is that if I draw the 2, I have to go all the way down here, next to each other, the traditional Gram-Schmidt algorithm, I want to try to get them together. The traditional Gram-Schmidt involves constantly looking back at all of my previous Q vectors and subtracting them from the vector I'm currently working on. Whereas the modified Gram-Schmidt involves the moment I find a Q vector, I sweep over all of the vectors ahead of it and subtract the component. So rather than looking back at your previous ones, you look forward and remove it from everyone ahead of you. And this is kind of a subtle distinction, but the idea is that the moment I find something that I can remove from vectors, I do it, and that causes the condition number to decrease because I've gotten rid of redundancy in the vectors. So for example, if my first vector in an ill-conditioned case was my bearing direction, I immediately subtract that vector out from everyone, because if I have a dominant direction in my column space, in my first step of my modified Gram-Schmidt, I'm going to remove that from all the other vectors. So insanely enough, even though if you look at how this code is structured, it's basically a one-line modification, which is instead of sweeping over everything up to my current vector, I sweep over everyone ahead of my vector. That one modification actually totally solves this condition number problem. So this is this class implements both methods, and we confirm that they both give me the same Q and R, so nothing has changed. But if I then see how that affects this condition number experiment I was doing, for the case where I have a really, really high condition number, Gram-Schmidt gives me what I would argue is a relatively high error, but this modified Gram-Schmidt actually gives me close to my working precision. So this one line change actually stabilized my algorithm. And then they both give me the same error when I have a well-conditioned matrix. And this is basically just this idea that if all of my columns seem to point in the same direction, I immediately just subtract out that direction to make my matrix as well-conditioned as possible as my first step. And that's sort of how you rescue Gram-Schmidt. Okay, so I'm at time, so that's the main idea. I'll just mention that modified Gram-Schmidt really sort of encapsulates a lot of the ideas behind Krylov subspace methods. And the book talks about how you see the same basic idea pop up in a lot of other algorithms. So there's a whole chapter on this in the press textbook. All right, thank you.